Welcome.
Live streaming is on.
Welcome everybody to the last talk of the first day for Transform 2022. What we have to finish off day one is a tutorial from Thomas Ostersen of DataRock, and he's going to be assisted by Tommy Carmichael in the Slack channel, which I'll get to in a second. And this is about machine learning models in geoscience. So if you're unaware, this is part of Transform 2022, which is a virtual conference type thing around digital geoscience. Everything that we do is as open and freely available as we can make it. A large part of that is thanks to curvenote.com for their support of this conference. We also, if you're wanting to see what else has happened and what is going to be happening over the next few days, have a look at softwareunderground.com/transform to see the schedule. And if you're wanting to get involved with everything and ask questions, if you happen to be catching this live, join our Slack. That is at softwareunderground.org/Slack. Remember that even though this is a live stream, you can pause and rewind the video if you miss something. So don't stress about that if you miss something. This will be available afterwards as well. So please do share it if you find it useful. And with that, I'm going to hand over to Thomas Ostersen. And again, machine learning models in geoscience. So take it away, Thomas.
Cool. Thanks, Martin. I'll just start sharing my screen here. Bear with me 1 second. Okay. Can everyone see that? Yeah. All right. So, I guess first of all, just need to acknowledge the Software Underground team for putting this Transform 2022 conference together. It's a real privilege to be here, and yeah, I'd just like to thank the organisers. I believe I also need to thank CurveNote as well for hosting and supporting the presentation, the conference. So yeah, today I'm going to talk about some of the issues that I've come across in my journey to becoming a geodata scientist, I guess. And in particular, we're going to focus on an example, a prospectivity analysis example. We're going to look at how data selection with spatial data sets affects the application of generic machine learning models. So just for a quick outline, I'm going to cover the study area a little bit in a little presentation here, and then I'll just jump to the actual notebook and get started. We're going to discuss the tin-tungsten deposits that occur in Tasmania. I'll just cover the sort of the basics of the mineral prospectivity mapping workflow, and then there'll be some links to the notebook, the GitHub with notebooks and data. So in terms of the study area, this is the part of the world we're going to focus on. It's the northeastern corner of Tasmania, which is this little island south of mainland Australia. And this area is prospective for tin-tungsten granite deposits, granite-related tin-tungsten deposits. There are a number of granite-related tin-tungsten deposits in Tasmania. They are related to this to orogenesis that occurred in East Gondwana and the Devonian. All the deposits that have been exploited in eastern Tasmania have since shut down operations. I believe Aberfoyle was the last one to shut down in the 90s. But there is one deposit that's still currently being mined, and that's Renison. It's actually a tin skarn deposit, but it's nonetheless associated with these Devonian granite intrusions. So yeah, we're going to focus on this part of the world. And the reason we're going to focus on northeastern Tasmania is we've got good geophysical coverage with both airborne, magnetic, and radiometric data sets. We have pretty good gravity coverage as well. The geology is fairly simple. Basically, the rocks that are exposed on surface are a thick package of marine quartz turbidite, Mathina sediments, which are intruded quite extensively by these Devonian granites that we're interested in. And it's also a very nice part of the world. It's where I'm from, and you should definitely visit. So the tin-tungsten mineral system basically involves, or mineralization is related to, or occurs at places in the upper parts of evolved granitoid plutons where you have mineralizing fluids, the metal carrying fluids that are exhaled from a cooling magma that gets sort of ponded and focused. And this tends to occur at the upper parts of these intrusive bodies. And I guess before we can even sort of apply machine learning prospectivity analysis, we do need to think about the mineral system and how we might be able to exploit the geophysical properties or the geological properties of the system in order to inform our modeling workflow. So things that are important for this prospectivity analysis exercise is that the upper parts of these granite bodies, given that granites are low density, they tend to manifest as gravity lows. In addition to that, because they're quite evolved, they tend to have low iron titanium oxide content and thus manifest as magnetically quiet, meaning they don't have extreme high or low total magnetic intensities. And also when they're exposed, given that they're quite evolved, the prospective ones, you end up with fairly strong radiometric responses with high potassium, uranium, and thorium. So that's essentially the mineral system we're trying to target. And the way we're going to try and model all this is through this mineral prospectivity mapping approach. I've got a schematic diagram of the workflow here, but basically we can conceptualize mineral prospectivity as a function of this geophysical or of the geological, geochemical, and geophysical information that we quantify in these continuous raster data sets or evidence layers. And the goal of the exercise is to approximate this model, this function, sorry, with some statistical model, which is a problem that machine learning algorithms are well suited to. Of course, in order to fit a model, we need some points that represent known mineralization, which we've taken from point data sets, which are compiled by Mineral Resources Tasmania. And basically, we combine these continuous raster evidence layers with our occurrence points to generate a set of labeled pixels that are proximal or distal to mineralization. We then take that labeled data, we divvy it up somehow, we retain some for model training, which we then try to validate on a separate set of the data to get validation metrics of our model. And then when we've got the model, we can apply it to our evidence layers to derive some prospectivity map. And what we're going to focus on today is pretty much this data selection part of the workflow. We're not going to use any sophisticated models. We're just going to use a random forest classifier with just default settings. And yeah, that's basically the goal of today. So with that, I'll jump to GitHub, where all the code and the instructions to get set up are hosted. That's the link there. I've also included these some interesting and relevant reading. I'll save this presentation as a PDF and include it in the GitHub after the talk. This is what the GitHub page looks like. I've got instructions to get set up. You can download the data from a Google Drive link here. But I should say, if everything else fails, you can open this Colab notebook here, which will take you to a Colab notebook that I've set up with code to basically download the data sets, install some dependencies, and get you started. So with that, I'll jump to my notebook and we can get started. So I've just kind of duplicated a bit of the stuff in the presentation here. I've got a link to the data, and I have a roadmap here that'll just cover some of the high points. So the first step is basically just to load the data sets, which if you've downloaded the zipped directory and unzipped it, you can set a path to that and get started. So I've already installed, or I've already set it up to import some key libraries. NumPy is what we're going to use to manipulate the data. we're using matplotlib for all plotting. We're going to use some other libraries later on that I'll import later on. So run that. You don't have to do this, but I've just got some plotting parameters here just to prettify the output, basically. So to get started, set your data directory. And then I'm going to set my path to the mineral occurrence file. So set path to minox, point fn, os path join, data directory, smw minox gpkg. And then I'm also going to, I'll just add a few cells down here to give me some space. Make a list of rasters in the data directory. So we'll call that geotiffs because they're all geotiffs. We'll just make a list here. Join data here x for x in OS. List there. Here. If dot tiff in x, and we'll just confirm that we have these paths. Okay, so I've got my files here. Let's go ahead and read the mineral occurrence points into a data frame, and we're going to use GeoPandas for this, which is a pandas like tabular data library for geospatial data, for vector geospatial data. It's a really good library. Import GeoPandas as GPD. Read occurrences. df equals GPD. Read file point fn. Let's see what that looks like. Okay, so this is our mineral occurrence data set. This is taken from the Mineral Resources Tasmania mineral occurrence compilation. And what I've done is I've pre-filtered it to make sure that we have only occurrences that have tin in the commodities column. And I've also made sure to remove any alluvial deposits because we're targeting sort of in situ primary mineralization. So yeah, we don't want to include the transported placer type deposits in our prospectivity analysis because we'll end up with a pretty terrible model. We can plot those points, get a sense of where it all is. So yeah, there isn't much in the way of spatial context here. This is just our coordinate system. But yeah, I'll move on to reading the geotiffs into memory, and then we'll sort of plot everything all together to get a sense of where our data is. So let's go ahead and do that. To read data from the geotiffs, I'm going to use the Rasterio module, which is a really good library for reading geospatial raster data sets. I want to loop through every single raster we have in our data directory, in our geotiffs list. I want to read the data in their single band rasters, so read the single band of information and then append it to a list so we can build a 3D cube of geospatial data or raster data. I have pre-processed these rasters such that they are co-registered and have the same extents. So this process should be fairly straightforward. So let's read the geotiffs. So we'll set up an empty list, set up two empty lists to contain the data and the file names, just for plotting reasons. Okay, so let's loop through the geotiffs for fn in geotiffs with Rasterio open fn read as source. First, we're just going to read the transform, which will come in handy later. We're going to read spatial information. which we'll use for plotting in a minute. So first thing we're going to read is the transform. That's basically the transform that allows us to go from pixel coordinates to spatial coordinates. We're going to read a tuple I'm going to call region, which will contain the xmin, xmax, ymin, ymax, the bounds of the images. So left source bounds, right source bounds, bottom source bounds, top. And then we'll read band 1 data into the variable d. Let's read band 1. We'll also read the no data value. Well, we'll make a no data mask because there are regions of these data sets that contain no information. And to do that, we'll go no data mask is where the raster d equals the no data value. We'll then mask that equals with a man, and then we'll append data to lists. So data append d, and then names append. We'll append the name of the file stripped of the file extension. So os base name fn replace .tiff with nothing. Okay, let's just see if that's worked. Data names, no bugs. Okay, so we've got a list of arrays, and at the bottom of that we have a list of file names corresponding to what that data is. So let's just stack the data, the list of arrays into a 3D stack of arrays. Stack list into 3D numpy array. Data equals np stack data. Now let's go data. Let's look at the shape and we'll see the names as well. Okay, so we have a 3D data set, 3D numpy array with 7 bands of information corresponding to these file names, and then we have 2,600-ish y coordinates and 1,800 x coordinates. So cool. We've read the data in the memory. Let's plot it because we need to sort of get a sense of where all this data is in space. So plot data. So we'll use a subplot array. Go 3 by 3, big size. Let's make that 12 by 18. And we're going to loop through a flattened. We're going to loop through axes in this subplot, in this 2D subplot array, 1 by 1. So for I ax, we're going to enumerate axes flatten. Need to put an if statement here. Make sure that we're not going out of bounds of our 7 bands. Data shape 0. Ax in show data I. Else, if there's no data to plot, we'll just turn the axis off. Okay, so you can see the coastline there where we've got no data. There's also a bit of missing data down the bottom there. The color stretches are just currently stretched to the min-max values. So let's just set the title here and replot that. Whoop. And let's stretch the colors to 90% of the data. So vmin equals np-man percentile, data I 5th percentile, and the vmax equals np-man percentile, data I 95. That should stretch the colors a bit better. Yep, there we go. Okay, so the data sets we have available to us, we have two gravity rasters. This one, the top left, is the isostatic residual. We then have the first vertical derivative of that. We've got total magnetic intensity, first vertical derivative of total magnetic intensity. We have radiometric channels K, thorium, and uranium. But where are our occurrences? Let's add our occurrences to this. And you should know, so at the moment, the coordinates on these IMSHOs are just pixel coordinates. So we need to add an extent, and we can use that region tuple for that. And then we'll add the occurrences. So df plot axis equals x. We'll use a star marker, and we'll set the face color to white. Okay, so that's where our occurrences are on this raster data. And you'll note that they seem to occur in the sort of low density regions of the map, given based on this static residual. So yeah, I mean, that's basically where the granites are. You'll also see that they sort of occur in these quiet parts of the total magnetic intensity image. This sort of this area here in the southwestern corner of the data set, that's where we've got post-carboniferous sort of cover sequences or sediments that have been intruded by dolerites. So these like strong magnetic responses are related to these dolerite sills. And yeah, obviously where they occur, we're not really prospective for tin-tungsten. Occurrences also, the tin occurrences also co-occur with regions with sort of high radiometric responses, strong radiometric responses. Cool. So after all that, we've read all our data into memory, and we can start to think about, modeling. But in order to do that, we need to basically label these pixels with, whether or not the pixels are proximal or distal to our mineral occurrences. So we need to rasterize our vector point sets. So to do that, we're going to use the rasterize module from Rasterio. Rasterio features import rasterize. And then this rasterize module takes a geometry generator. So we'll just create that, which looks like this. So we have the geometry and then a fill value for geom in data frame geometry. And then we can create an output. We can create a labeled raster array we can call labels, which is the output of the rasterize module. And the input shapes are the geometry generator. The out shape is equivalent to the shape of the no data mask, or even just data band 0, all the same shape. The fill, the background will be 0, and it also needs a transform, which we have as transform. So let's just plot that and show labels. Oh, let's actually add the no data. Let's just nullify the offshore pixels just so we can get some spatial context. Labels, no data mask equals man. Oh, and I think I need to make that as type load 32 for the mans to work. Sorry, this is a bit. Okay. We haven't rasterized anything just yet, and that's because we're trying to rasterize points. What we need to do is convert our point set into a polygon set, and we can use this one-liner from GeoPandas to convert the points into little circles. We can add, so we'll buffer the points by say 10,000 meters. If we rerun that, we get this. So basically we've created a label, we've created a new raster where the background pixels are 0 and pixels that are within this buffer distance of our occurrences are 1. And And this is a point in the whole workflow where we need to start making some decisions using some a priori, geoscientific knowledge. If we want to, I mean, we want to build a model that is sensitive to, you want to build a model that can tell you that you're proximal to an occurrence. And implicit in what we've done here is we're basically saying that distance in x and y directions is the same. We have a Euclidean proximity metric, basically. Probably not a super valid assumption with this mineral system, but I can think of other systems where it's definitely not valid. Like, let's say you're in a structurally hosted gold system where, proximity along strike of mineralization is different to proximity across strike. So you might use like an anisotropic distance metric to define what is and isn't close to mineralization in that situation. But for our purposes, this Euclidean buffer metric is good enough. And also, the actual distance that you're using is important too. So given that we're sort of dealing on a regional scale here, I think 1,000 meters is it's good enough. But this is definitely a decision point that you need to consider and maybe even test when you're developing prospectivity models. So we're going to stick with that. We'll say that if you're a pixel within 1,000 meters of an occurrence, you're proximal, and if you're not, you're a distal pixel. And that's our two classes that we're going to use to train a model on. So cool. So we've got our data, we've got our label raster now. The next thing we need to do is convert this 3D data cube and the 2D raster label set into a format that these generic machine learning models can read. And we're going to use a random forest classifier for this. So the random forest classifier I'm going to use takes two inputs, an n samples, n features array, a 2D array, and then a 1D array with labels corresponding to the n samples. So we need to convert the 3D array into 2D. Let's go ahead and do that. Convert 3D data cube to 2D tabular array. And in machine learning world, the capital X variable is usually used for these types of things. I'm going to call it xpix. And we're going to go data, reshape, and it will take a tuple. I'm going to say the first dimension will be the number of bands, so that's shape 0. The second dimension will be the result of multiplying shape 1 and 2, so the number of x columns and y columns. Data shape 1 by data shape 2. Let's have a look at the shape of that. Oops, shape. Cool, so data shape. Okay, so the original data set was this 3D cube. We've now reshaped it to n bands, n pixels. We've got about 5 million pixels, thereabouts. But to input it into the random forest classifier, we need to basically swap these dimensions around. So we'll just transpose it. And now we have n pixels, n bands. Cool. Let's build a label set for this. So again, machine learning world, they use like a lowercase y for that. So we'll take the labels array and we'll just flatten it. And then just print the shape of that. Okay, so we have 5 million pixels, 7 raster bands, like 7 data layers, evidence layers, and 5 million pixels with labels in them. But this still contains nulls, contains nans, which we can't put into a random forest classifier. So let's remove nans. So, and I'll do this, I'll just output an x and a y array for this. So x pix, y pix, hold on, what am I doing? Oh, yep. NP is nan, so the inverse of NP is nan, y pix. That'll do. Y equals y pix. Oops, the same. Okay, so let's just confirm that. Okay, so we've gone from 5 million pixels to about 4 million pixels. So we basically just removed all these pixels here that contain no data. And now we have a X data array and a Y labels array, 2D X data array, 1D labels array. Sweet, we're on our way. We can actually fit a model for this now. So let's do that. Let me just consult my notes briefly here. Give me a second. Right. Let's just put some markdown in here. Train models. Okay. Import modeling modules. We're going to use scikit-learn for this. So from sklearn ensemble import random forest classifier from sklearn model selection import train test split. So before we fit a model, we want to be able to validate that model. If we go back to the presentation, you remember, once we've got our modeling ready data set, we need to extract some of it, hold it outside of the modeling process to use as a validation set. So to do that, we're just going to use this train test split module, which basically just allows us to split the input data set into a training and testing subset at random. So training and testing subsets. So we'll go X train, X test, Y train, Y test equals train test split X, Y test size. So let's go, we'll split it in half at random, random state 42, 0. Okay, so let's now define a model. Okay, model 1 equals random forest classifier n jobs equals -1. So this is we're just instantiating a model object here. I'm just setting this n jobs -1 so it parallelizes the training process. And then we can just fit the data, X train, Y train. Whoops, did I mistype that? Yes, there we go. Okay, that's training now. It might take a while on some machines because we're feeding it 2 million pixels, so it's a fairly large job. Okay, so while it's training, let's talk about how we're going to validate it. So let's well, given that it's a binary classifier, we can look at we can use a receiver operating characteristic curve to sort of get a sense of how well the model is performing on our validation set, which is the test set. So we'll import metrics from sklearn for this. From sklearn metrics, my model's finished training. Import RSC curve and area under curve. So let's evaluate model on test data. So we're going to get a prediction. We're going to predict onto. So we're going to get our probabilities for class 1, which is our proximal class. Model 1 predict proba X test. Now let's just look at the output shape of Y proba. Whoops, what's going on here? Let's type that. Okay, so it outputs a 2D array. And what it's doing there is it's giving us the probability of class. So it's n pixels in our X test data set. And it outputs, in the second dimension, it outputs the probability of class 0 and probability class 1. So we will take probability of class 1 as our probability for proximal. We'll then calculate the false positive rate, the true positive rate, and the threshold we don't actually care about. RSE curve, Y test, Y probber. Cool. Okay. And then we'll calculate the area under the curve. AUC, PPR, sorry, FPR, PPR. Okay, plot all this. We'll just plot it on a subplot here. Big size, 5 by 5. Whoop. X plot. We'll plot the false positive rate against the true positive rate, and then we'll label it with the area under the curve. AUC equals format round rock AUC 2 decimal places. X, we'll plot a flat line as well. This will all make sense once we plot it. Make that a red line. X legend. Sure. Okay. So what we've done here is we've taken our model, we've predicted on the test set, which was a subset of the data that the model was not exposed to in training. We've calculated the true positive and the false positive rate, prediction rate. And then we've calculated the area under the curve, and we've got this plot. So basically what we're seeing here is some measure of model performance. And if you just had a coin toss classifier, if you're just going random chance, is this pixel proximal, is it distal, you'll end up with a blue line that kind of matches this red dashed line here. But we're getting pretty much a right angle, which means that our classifier is basically perfect, which is it's suspiciously good. So that's cool and all. Let's now do the other part of the workflow I showed in the slide earlier, where we apply the model to all pixels in the data set to derive a probability map for the proximal class. So let's go ahead and do that. But before I do, I'm just going to define a function to get the probability map, because we'll be doing this a little bit. We're doing this a few times in this tutorial, so we'll just get that out of the way now. Define a function to get probability map. Define get probber map. So we'll take the X pix array, which is the 2D array that still includes the nulls, the no data mask, which is a raster with the no data Boolean mask. Give it a model. So the first step will be remove nulls. X equals X pix np invert no data mask flatten, because it's just to make sure the shapes are appropriate. We'll then get predictions. So predictions equals model predict probber X. And again, we're only interested in the probability of class 1, the proximal class. The next step is to create an output array. We'll call it pred R equals np zeros shape equals no data mask flatten shape. So we're just going to make a 1D array for now. Make the D type, the data type float 32 to match the outputs of the model prediction. Okay, now insert predictions. So pred array, the inverse, invert, no data, mask, Latin equals predictions, reshape, spatial, pred r equals pred r reshape, no data, mask, shape. Then let's just test to see if that works actually. Get prober map xpix, no data mask, model 1. Oops, random forest classifier, predict prober. Is it working? Yes. Okay, so now that we've reshaped the prediction array, let's mask the no data. np man, and let's return it. Pred array, and we'll go pred r1 equals this. So let's look at that. Cool. So we have trained the model on a subset of all the pixels in our data set to differentiate between the distal and the proximal pixels. And then we applied that model to all the pixels in the data set and extracted the probability that the model thinks a given pixel is proximal. And you will note that these probabilities are pretty well centered around basically, I mean, this is almost a carbon copy of our labeled array. So, you know, we've got amazing performance metrics. We've got what looks to be a carbon copy of our labeled array. So, you know, we're overfitting this model massively, and it seems the model is biased towards. Well, I mean, the issue is there's a lot more distal pixels than there are proximal pixels, and that results in a bias towards the distal response. So what we need to do is think about how we train this. We need to think about the classes that we're training the model on, and what we need to do to try and improve this is to stratify the classes. So let's go ahead and do that. When I say stratify, I mean we need to balance. So for the model training data, we need to balance the number of pixels in the background class, the distal class, with a number of pixels in the proximal class. And often in these types of applications, we'll end up with a whole bunch more pixels in the distal than the proximal. So thinking about how you balance the classes in these types of workflows is kind of a big step. And there's a number of ways of going about it. We're just going to use a random undersampling exercise. So what I mean by that is we're going to randomly undersample the distal class such that we have the same number of pixels as the proximal class. Let's go ahead and do that. In order to do that, we're going to need we're going to import the random undersampler module from the imbalance learn library. So import random undersampler from imlearn undersampling, import undersampler. Yep. I'll just have a few more of these. Right, so stratify classes with random undersampler. So first instantiate a random undersampler here, which is called Russ, random undersampler, random undersampler, random state 42, X strat, Y strat, stratified, Russ fit resample X, Y. So let's have a look at what that does. So we go from 4 million pixels to this many. What's that? 200,000-ish. So this tells us that we have about 100,000 pixels that are proximal, and then the random undersampler has basically said cut down the majority class, which is the distal pixels, such that you have an equivalent number of background pixels or distal pixels. So now that we've done that, we can train a model again. So let's do exactly that. First, we need to we need to split it into a training and testing set. Generate training and testing set. X train, X test, Y train, Y test, Y train, test split, X strat, Y strat, test size. We'll go with a smaller test size. We'll keep a third for testing. Random state 42. Okay, and then define model and fit it. Model 2 equals random forest classifier and jobs minus 1. Model 2 fit X train, Y train. Should fit a lot quicker now because we have a lot fewer pixels. Cool. So that worked pretty well. Let's look at our receiver operating characteristic curve. I'm just going to copy paste because we've already done that. No need to repeat the typing of that code. So let me just double check that I've done this correctly. Yeah, we're getting the predictions, TPR threshold, yep. And then we'll plot that there. Cool. We still have a pretty well performing, pretty good model. It's performing really well. We've stratified the classes. What does the probability map look like? Let me just copy that code to predict. Sorry about all the scrolling. Okay, predict array 2, model 2, imshow red array 2. Okay, that's given us a different result. We're getting some, probabilities that you're proximal, sort of distal to our training area. So that's kind of encouraging. You could look at this and go, oh yeah, bit of probability down there. That's a good result. But our performance metrics are still really good, and this brings us to the issue of spatial data leakage and the effect of spatial autocorrelation. The problem here is that we've stratified our classes, and then we've randomly selected pixels for model training and testing. And because we have geospatial data, that data is affected by spatial autocorrelation, which is basically the tendency for pixels that are proximal to one another or close to one another to be more alike than pixels that are far away from one another. So if you think about it, when you randomly select a pixel for testing, it is likely that that pixel is right next to a pixel that you use for training. And because of spatial autocorrelation, those pixels are likely to be quite similar. So you're essentially validating your data, your model, on data that is very similar to the training data, and thus you end up with these overly optimistic validation metrics. You're basically violating an assumption of independence here. And this is a real problem with modeling geospatial data. And there's a number of ways to deal with it, try and figure out what the true performance of your model is. And we're going to go into a couple of them now. So the first one we're going to do is we're going to try and separate our training from our testing data spatially. And in order to do that, I'm going to nick some code from Stack Overflow here with this beautiful function. So this is a make checkerboard function from my guy, blubberguy22, posted March 17, 2020. Basically, this function just takes a board size, so like a raster size, and then the size of your squares, and outputs a checkerboard. So let's look at that now. So let's make a checkerboard pattern. We'll call it checker. We'll make checkerboard. I need to just change the data type here. Float 32. Yep. So the input, the board size is the size of the no data or the data band 1 shape. The square size, let's go with, I don't know, 1,000 squares by 1,000. So 1,000 in X dimension, 1,000 in Y dimension. Which, because we have 5 meter pixels, that's 5 kilometers. Let's mask the checkerboard. No data mask. NPN. And plot it. Big X equals 10. X show checker extent region df plot x marker equals this one base. Oh, let's go with red. Okay, so now we have this checkerboard pattern that will allow us to select data from here to train a model, and then we can validate it on data from a different checker. 1,000 might be a bit much. Let's go with 500 pixels. Okay. I kind of want to isolate that little spatial cluster of occurrences. So let's go with 250 pixels. How does that go? No. 400. Bear with me here. Okay, there we go. So we've isolated that one, that little cluster. And we want to see if that little cluster gets predicted when you train a model on pixels from this yellow checkerboard. So, okay, let's go ahead and select some data using this checkerboard. This is going to be a bit verbose, but just bear with me. So split data into checkers. Right. X check 0 equals, let me scroll down here a bit. X pix. Hold on a minute. Yes, X pix checker flatten. Is it called checker? Checker, yeah. Checker flatten equals 0. Y check 0 equals Y pix checker flatten equals 0. I'll just duplicate that for checker 1. Whoop. I'm using my mouse for coding. How embarrassing. Okay. Let's remove the nulls, the nans. X check 0 equals X check 0, Y check, the inverse NP is nan, Y check 0. Y check 0 equals Y check 0. Okay. Okay, that looks about right to me. Is that right? Yes. Okay. So now let's just print some information here. I'm just going to copy paste this just for simplicity. So we're just going to print some information here about the shape of the arrays. So we've got 200,000 odd pixels, 7 bands, 200,000 odd pixels in each each checker data set. Okay, so now these are still going to be imbalanced because there's still more proximal than there are distal pixels in this checker pattern. So we need to run undersampling. So let's go ahead and do that. X check 0, Y check 0 equals Rus fit resample. X check 0, Y check 0. And we'll do the same for this one. Print that again. Cool. Now that should give us, yep, so this is the raw data. This is after undersampling, random undersampling. So we have, 100,000 odd pixels for each checker. Let's fit some models. So we'll go model 3 equals random forest classifier and jobs -1. Model 4. And on model 3, we'll fit it to X check 0, Y check 0, 1, 1, 4. Okay, so we're fitting 2 models there, 1 to each checkerboard. And let's have a look at the validation metrics. So we're just going to loop through our models, our checkers, and calculate the metrics and just append them to a list. So get ROC curve data. So we'll just instantiate a list here. And we'll for model X check, Y check in zip. Let's put some lists in here. Model 3, model 4, X check 1. That's correct. So for model 3, we're going to validate it against checker 1. And model 4, we'll validate it against checker X check 0. Do the same for the Y checks. Check 1, Y check 0. Yeah, this is very verbose. Apologies for that. Right. Y pred equals model predict probber X check. Take probabilities for class 1. FPR, TPR, and a threshold we don't care about. ROC curve. Y check. Y pred. ROC AUC, area under the curve. AUC, FPR, false positive rate, true positive rate. And let's append all this as a tuple to the list. ROC, data, append, FPR, TPR, ROC AUC. Plot all this. So big X subplots, big size 5x5 for I, FPR, TPR, AUC, not AUC. In enumerate data X, FPR, X, FPR, TPR, label checker AUC equals, and then we'll format I, because we use the model 3, which was trained on checker 0. Yep. Round AUC, rock AUC 2. X plot. What's that? A dash line. Bear with me here, we're nearly there. Whoops. I always get that one wrong. Cool. Now, Axe legend. Okay, so now we've got, you know, we don't have that straight dog leg right angle. We've got, I guess, what looks to be more realistic performance metrics on our spatially separated validation data. Yeah, I mean, this looks a bit more realistic, and it's what you'd expect because we've made sure that our testing and training data have been spatially separated. So yeah, I mean, let's have a look now at how these. Let's have a look at what the models look like. So we'll use our. Oh, sorry, I'll have to scroll up and find the name of that function. Bear with me. Get proper map. So predict. Generate maps. So pred R3 equals x6, no data mask, model, it was model 3, and R4, get, come on, 4. Now let's plot these side by side. Plot probability maps. Big ass subplots. 1 row, 2 columns. 10 by 10. Yep. For I. Array in enumerate. Red R3. Red R4. Axe I. Imshow extent region. Let's plot our occurrences on these as well. df plot axe equals axe I marker star. Let's go white. That should just work. So we're predicting onto these arrays for each of those 2 models, and then we're having a look at the results. Okay, it's kind of these occurrences are kind of obscuring the results a bit. Let's just comment that out a bit, and let's look at these 2 probability maps. Cool. All right. So they're kind of different. This first model, so this was model 3. That one was trained on, let's just confirm, let's have a look at the checker again. Yeah, so that one was trained on checker 0, and you can see that occurrences up here in this northwest corner, you know, they get predicted, and that's because they were included in the training data. When they were excluded from the training data, didn't get predicted at all. So yeah, I mean, this is an important point. If you don't spatially separate your data, you don't really get a sense of, you don't get an accurate sense of how well it's performing. Yeah. That little cluster, that little spatial cluster of occurrences doesn't get predicted at all. So we can build on that, and we can do a similar exercise again, but instead of using a checkerboard, we can cluster up our occurrences, train a model on all but that cluster, and then predict. And then we can sort of validate how well that model is performing when you're holding out occurrences that you care about. So let's go ahead and do that. So first of all, what we need to do is cluster up our occurrences. So let's just, I'll just plot them here just so we can see what I'm talking about. So our occurrences occur in these, spatially clustered, I guess, mineral camps or mining camps. There's probably about 8 clusters here. And what I want to do is basically cluster them up. So let's say we want to train a model that excludes all of these. So we'll say, okay, let's build a model that is trained on all these other clusters. Without that, we predict and then we check the performance in this little area here. We do the same for every single spatial cluster. So before we do that, we need to generate spatial clusters, and we can do that with k-means. So let's do that now. Import k-means. So from cluster import k-means. Get occurrence points, xy points. So we need to get the occurrence into a point set. We'll just do some list comprehension for that. So geometry x, geometry y, or geometry and df geometry. That just gets us, what does that look like? Okay, so that just gets the x and y coordinates for each of our occurrences in our data frame. So now let's get a k-means object. Let's instantiate a k-means object. K-means, I reckon there's about 8 clusters, so we'll say that n clusters equals 8. And we'll fit that to our xy points. Okay, and then we'll append to the data frame a new column, and we'll just call it labels. And that will contain object labels. And because k-means has a cluster 0 and our background class is 0, we're just going to add 1 to that. So let's just see what that looks like in the data frame. Okay, so we should have appended a column. Yeah, so we've appended a column labels, and they contain numbers for the cluster. Let's visualize them spatially. So we'll just go plot clustered points. For C in df labels unique, let's sort that. So we go from have increasing numbers. df labels equals C plot x. Okay, oops. All right, there we go. So we've added a cluster label to our occurrences, and we can then use these cluster labels to generate a new raster label set for model training. So let's go ahead and do that. So let's make a new raster label. Generate raster label. So we need a geometry generator again. Equals geom C for C geom in zip df labels df geometry. That should work. Call it cluster map equals rasterize. This is that raster module again. Shapes equals geometry generator. Oh, we need to buffer it. Buffer by, what do we say, 1,000 meters. Yep, that'll do. Out shape, no data, data 0 shape, which is our raster shape. Fill 0, that's the background, the distal pixels. Transform equals transform. All right, let's look at this map and show cluster map. Okay, well, let's apply the nulls mask. Cluster map, no data mask. What's going on here? Oh, data type, it's all wrong. As type, float 32. Okay, there we go. Okay, so now we've got, this is our labeled raster dataset where pixels that are proximal to occurrences are given the same value as the cluster number, basically. So we can use this to select our training data, and we can do it such that we hold out a cluster at a time. So let's do that. We're going to have to write some functions to simplify this process. This might take me a while to type out, so just bear with me. But the first function we need to write, we're going to write a function for basically data selection. So define cluster data selection function. Def cluster pixel selection takes the cluster map, the data cube, or actually the 2D array, class 1 list. So we're going to give it a list of values that are in class 1. So in this case, if we want to train a model that holds out this cluster, whatever number that is, we can feed a list of numbers that correspond to these clusters here. So let's do that. So let's flatten let's make a Y array, which is just a flattened cluster map. Next step is to remove nulls from the xpix. So we'll go x equals xpix inverse np is man y. We'll do the same for the y. Okay, next step is to rename pixels in this y array. Actually, no. Rename pixels that's in this y array that are in our class of interest. So to do that, we go y np is in y class 1 list equals 1. So any classes that we pass in this list get converted to 1. And if y is not 0, make it 0. So this step will basically say any class that isn't in this list gets converted to background, which is how we hold out one of our tests. So we're kind of putting it in the background class. So this is like a test for whether you'd find it if it was in the background. Hope that makes sense. It'll make sense in a second. X, Y. So that function selects our data. Let's just write a function to fit a stratified, define stratified random forest function. So fit strat forest x, y. Oops. X, y equals, oh, we need to fit, we need to give it the random undersampler. X, y, model equals random forest classifier, and jobs is -1 for multi-threading, and we'll return the model fitted to X, Y. Okay, that's 2 functions down. The last one is holdout rock AEC. So define a function to validate model on holdout class. So this one basically takes the model, the data or the cluster map, the classes you use to fit the model, and the holdout cluster number to generate validation metrics for the occurrences that you held out of modeling. So let's do that. Cluster map takes cluster map, takes the X pix, takes holdout cluster list, model cluster list, model. Okay, so again, let's flatten the cluster map. Geez, I hope all this works. X equals, oops, G is nan, Y we're just dropping the nulls here. X equals yep. So now we're going to remove from the data the pixels that are in our modeling cluster list based on our label set. So NP is in Y model cluster list Y same thing, right? And then Y equals is in Y holdout cluster list equals 1. So we're just renaming pixels that are in our holdout cluster to 1, which is our, I guess, target cluster. Y model. So now we go Y pred equals model predict robber X probabilities FPR, same old ROC curve Y pred rock AUC equals AUC false positive rate, true positive rate. Return FPR, TPR, rock AUC. Okay. Cool. With those functions defined, now let's if I just go up to this map again, let's just bear with me here for a sec. Labels C. Oops. Legend. Let's just see which cluster's which. What's going on? Doesn't matter. Forget about that. Let's just pick a cluster at random and hold it out of the modeling and then predict on it. So let's hold out cluster 5, cluster 4. That'll do. Select data, cluster pixel selection, cluster map, xpix, and we're going to use class 1. So that'll basically, sorry, class 4. So we're going to use we're going to develop a training set that excludes cluster 4 from the target class or from the proximal class. Fit strat forest x, y, FPR, TPR, rock AUC equals holdout rock AUC, cluster map x fix. So the holdout cluster list is 4. Model cluster list is all but 4. So that's 1, 2, 3, 5, 6, 7, 8. And the model, did that run? No, it didn't. Ah. Bear with me here 1 second. Hit example. Right, I'm just going to copy paste because I've buggered that up. And let's do it. So in this case, we're going to hold out cluster 1, and we're going to predict using pixels from all the other clusters. The wheels are falling off here, folks. Okay. All right. I managed to get that working. Okay. So apologies for that. So what we've done here is we've trained a model on all pixels, on pixels surrounding all our spatially clustered occurrences, except 1. And then we've generated these validation metrics on cluster 1. So we can see that it's not performing too well in that case. Yeah, and you know, I think what we should do next is let's loop through every single cluster of our occurrences, train a model that holds that cluster out, calculate our metrics for it, and then look at them. So let's go ahead and do that. So let's go loop through loop through clusters. So first we need to create lists for our outputs. Let's go models, and put in this list. How much time? No, just a little bit. FPR, TPR, rock ACs equals empty list. For I in data frame labels unique. Again, let's sort that. Let's just print that to make sure it's working. Yep. We'll select the data. Cluster pixel selection. So our function is slightly different here. Cluster pixel selection. Okay, so it takes the cluster map, the data cube, cluster map data, and the class. Sorry, the modeling classes. So that is all the classes except the one we're currently looping through. So that's just J for J in range 1 to 9. If J is not equal to I. That just gives us a list of modeling clusters to use. Model equals fit stratified random forest X, Y, FPR, TPR, AUC equals holdout rock AUC cluster map data I, which is the validation cluster we're using, and then this is the cluster we're using to fit the model to, and then I believe that takes a model. Okay. Oh yeah, we need. Oh, that's fine. Models append model. FPRs append FPR. TPRs. Oh yeah, should put S's there. Append TPR. AUCs. Append rock AUC. Okay, hopefully that works. So we're looping through our spatially clustered occurrences. We're training a model that excludes from the training data pixels surrounding that occurrence, and we're generating performance metrics for that held out occurrence. Next, let's plot this. So this will be the last plot, I think, second to last. For FDR, TPR, rock AC. Let's okay. I can enumerate zip FPRs, TPRs, rock ACs. Okay. X plot. God, I hope this works. Label cluster is I plus 1. AUC equals format. Whoops. I plus 1. Rock AUC. Let's just round that. Rock AUC 2. Hey. Okay. I think it worked. X. Let's just plot a dashed line here. 1. Let's make that 5 be 5. Eight by 8. Okay, now I think there's a bug here somewhere. I don't believe that cluster 1, but the others I do believe. So I guess what we're seeing here is that we get very different performance metrics for this model for the various clusters when you exclude them from training. And in one case, cluster 6 here, it's actually, worse than a random classifier. And if I were to guess, I'd say cluster 6 is the cluster that is way up north, far away from all the other clusters. So we can just confirm that. Actually, no, I can't. I'll have to scroll up and have a look. Sorry about that. Yeah, this brown cluster up here, that's cluster 6. And that's the one that has the worst. It's just not really identified at all when it's excluded from the training data. So tell you what, let's apply the models. Let's get probability maps for all of these models and look at them. Let's do that. This will be the last plot, I reckon. Loop through models and get probability maps. Prob maps list for M in models. And we'll just use the prob maps. What's the function? Prob maps. And is it get prob map? Sorry, folks. I'm just going to have to scroll up, find my function. Get prob map. That's it. Right, here we go. So we will, in here, append the output of this, where the model is M. So we'll just tuple index out of range. What's going on here? M in models. Did I append the model? Oh, I've defined the wrong function here. I just need to go back and, when I copied and pasted, I buggered it up. So just give me 1 second. I'll just okay, that's the one we want. And I'll scroll back down all the way. Yep. I'll just wait for that cell to finish. And then I will loop through my models or my probability maps and visualize them and plot them. So let's do that now. So plot or models. Let's just confirm that's actually worked. Prob maps. Yeah, cool. Okay, so we've got a probability map for each of our models there. Big X equals, we've got eight maps, so we've got a 4x2 plotting array. Subplots 4x2. Big size. Oh, bloody 10 by 20. For I, let's make that axes. I, ax, enumerate, axes flatten. Because there's 8, that should be fine. Image equals ax and show prob maps I extent equals region. Let's see if that works. Okay. Let's make that 30. Okay. Not too many holdouts. Oh, did. Yes. So it's a bit hard to see, but basically, I'm pretty sure this very first model. Let's just add a label here. I1. Okay, pretty sure this model 1, which was meant to hold out cluster 1, didn't work. I must have screwed up the data selection function there. But this one, model 2, has held out the occurrences just here, and we can see, that's substantially different from that one. And yeah, when it's held out, you obviously don't get, the same pattern, but you do get some, prospectivity or probability that the model thinks the pixels are proximal in that area. This model here has held out pixels in this spatial cluster around here, which you can see in model 4 there. Again, places some prospectivity in that area. Model 4 here has held out these occurrences in the sort of southernmost cluster. Again, places some prospectivity, but yeah, it's not as good. this model 6, this is the model that held out that northernmost cluster of points. No prospectivity or probability that the model thinks is prospective in that area. Yeah, and so on. So I think that might do it. I'm sorry about the verbose code and the error there and copy pasting. I'll clean up the notebook on GitHub, and you can look at it there. So yeah, I guess that's it from me. Not sure what to do now. Are there any questions?
I just realized I'm probably muted. Can you hear me now?
Yes, I've got you.
Sorry, I was going to say we've got a little bit of time. So what I think we will, there's one question from Lucas, which Tom has answered, but maybe you want to put it in the video as well. As far as I can tell from the notebook, aren't you dealing with a heavily imbalanced problem? In this case, shouldn't you rather use a precision recall curve rather than the ROC? I see that you do random undersampling on the entire data set and then trains test split, but this would also hide the class imbalance on the test set, no?
Yeah, I mean, absolutely. I just picked ROC because it was just a simple metric to use, and I just wanted to play around with different combinations of training and testing data. So yeah, I'll do that next time.
No worries. Okay. Then I think, unless there are any other questions coming up, I could see a couple of people typing, but I think they may have been trying to tell me that I'm muted, which I appreciate. But otherwise, thank you very much to both you, so Thomas to Thomas Ostersen, as well as Tom Carmichael, both of you from DataRock. I think this was a really interesting one. Obviously, there's a lot more to that you could be doing with this, and it's a good indicator. It's a good idea of some of the uncertainty that you may need to consider when somebody comes and says, "Hey, we've got a really good result on this machine learning problem, with spatial type things in general." So thanks very much for your early morning. Hopefully this hasn't completely frazzled you for the rest of the day. There's a lot more of Transform 2022 still to go. As I said at the top, thanks to CurveNote for helping out. Have a look at softwareunderground.org/transform to get a full schedule. It's the last one we have for today, at least where I'm living. There may be another one late evening for you, Osti. I'm not 100% sure. But thank you, everybody, for tuning in. Remember to share these videos. They will be made available, or they will remain available after the stream ends. So, if this is something that a colleague would be interested in, please do share them. And yeah, we'll see you on the next one. Thank you very much, everybody.